This video is going to be a very brief introduction to organic chemistry, specifically looking at characteristic features of organic compounds in order to prepare us to draw organic compounds using skeletal structure or skeletal notation. All right, so what is organic chemistry? Organic chemistry is the study of compounds that contain the element carbon. Okay? So if we look at all of the molecules that I'm showing here, these are all molecules in common items that you've seen around. Ethanol is the alcohol in wine. Methane is the gas that burns in a gas stove. Caffeine, a molecule we all know and love. Okay, and then capsaicin, which is an active ingredient in arthritis, pain relief. What all of these molecules have in common is that they all have carbons in them. And that's what's going to make them organic compounds. So let's look a little bit more deeply into what organic compounds contain. Okay, they will contain carbon, that's a requirement. And then most, not all, but most of them will also contain hydrogens. And recall that a carbon-hydrogen bond is nonpolar. And this is going to bring about very interesting properties in organic compounds. All right, so we're going to have carbon. We've learned that carbon can form 4 covalent bonds. We also learned that hydrogen can form 1 covalent bond. So what this means is that in organic compounds, since you're going to have many carbons, oftentimes what you will see are these 3 different types of bonding patterns for carbon. You will see carbon form a single bond to another carbon, and then to satisfy the octet rule, it'll bond to other hydrogens. Other times, the carbon won't form a single bond. Instead, it'll form a double bond, as I'm showing here with ethylene. Okay. Other times, it can form a triple bond with carbon. And then the remaining bonds to satisfy the octet rule will go to hydrogen. So these are going to be some common bonding patterns that you will observe between carbon atoms. Something else you will observe that is a common characteristic is that some organic compounds will exist as linear chains, which you're probably familiar with, okay? But sometimes they can form rings, or what we call cyclic compounds. Okay? So yes, you can have carbon binding in a chain like this, or it can just bond to each other in this triangle type of structure. Okay? So what this means is that in a single molecule, like capsaicin, which was the active ingredient in the arthritis pain relief medication, some parts of your molecule could be cyclic, and other parts can be linear, as shown here. Okay, so organic compounds, again, they must contain carbon, that's a requirement. But sometimes they will contain other elements that are not carbon and hydrogen. Okay, so when they do not contain carbon and hydrogen, these are called heteroatoms. Okay. So some common heteroatoms are going to be nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So basically nitrogen, oxygen, and some of the halogens, or the halogens. What they all have in common is that they all have at least one non-bonding lone pair. Right? So that means that the common bonding patterns you will observe with nitrogen is going to be 3 bonds and a lone pair. With oxygen, you will often see it as 2 bonds and 2 lone pairs. And then the halogens, of course, will have 3 lone pairs and a single bond. So now, the most common multiple bond between carbon and a heteroatom is going to be a carbon-oxygen double bond, as shown on the right-hand side of your screen here. Okay, so this carbon double bonded to an oxygen is actually going to be part of the basis in a lot of the functional groups that we are going to discuss in this course. Okay, so the fact that carbon double bonds to oxygen is what is going to give organic molecules a lot of their reactivities. All right, so other than carbon being double bonded to oxygen, there are some other features about organic molecules that we need to be aware of, and that is the shape that they take. We've talked about Vesper theory, and with carbon, since carbon can form 4 bonds, it will be able to adopt different shapes in 3 dimensions depending on how the carbon is bonded to another carbon. So for example, in this first one, we have methane. Okay, that's just 1 central carbon. It's having a single bond to each hydrogen. And so that's going to be your typical tetrahedral structure. Here in this depiction, the wedge, the solid wedge is coming towards you, and the dashed wedge is going into the screen. Okay, these are going to be in the plane. So that is kind of the arrangement in 3 dimensions. Okay, then we have ethylene. When carbon double bonds to another carbon, this carbon here on the left-hand side is now going to be bonded to 3 different groups, and that's going to give it a trigonal planar shape. Okay, And then lastly, when carbon triple bonds to another carbon, you can see here that this is going to be a linear shape. So when we're talking about organic molecules, we will often be thinking about the shape around a central carbon. And lastly, this is the summary of all of those shapes that we have talked about already. The emphasis here is in thinking about what these bond angles are going to be, and also recognizing that carbon, when carbon is the central atom, it will either take a tetrahedral shape, sometimes a trigonal planar if it's double bonded to something else, typically oxygen, and other times it might be linear if it's forming a triple bond with another carbon, for example. The trigonal, pyramidal, and the bent shapes, trigonal pyramidal will often see it with nitrogen, and this one will often see it with oxygen. And that's just because nitrogen can form 3 different bonds and it has 1 lone pair, and oxygen can often form 2 bonds with 2 lone pairs. So now these angles here is just for you to keep in mind. It is something that sometimes we will use to think about how these molecules are arranged in space. Okay. All right. So with all of that, those main features and main characteristics, you will now be ready to start depicting these organic molecules, which sometimes can be very large and very complex, in more concise ways. So up to this point, we have been drawing molecules like this, where we draw out all the carbons and then all the bonds to anything else. In this case, it's all hydrogens. Okay, we've seen a little bit of the ball and stick model in order to be able to show what these molecules would look like in 3 dimensions. But now we're going to start using more condensed structures, which are going to give you basically the bonding pattern, how these are bonding together in a condensed way. But even more efficient and more practical is going to be these skeletal structures. And this is what we are predominantly going to use in this course. In the next video, you're going to learn how to draw these skeletal structures and how to interpret them, because this is going to be the most practical way to draw very large, complex molecules.